Greetings, fellow nerds. I've been continuing to research the production of sodium metal these past couple of weeks using the alcohol-catalyzed magnesium reduction approach. We had lots of problems, but we worked through them, including trying to find a workable solvent, reaction times, processing methods of dioxane, preventing glassware destruction, trying to dry the solvents using easy-to-obtain drying agents like aluminum and lithium metal, putting together our research into a mechanism, and finally finding some very easy to obtain off-the-shelf catalysts like menthol, tetrahydrolenol oil, dimetol, and borneol. Menthol in particular is a massive breakthrough in that it's extremely ubiquitous, and this makes sodium production easy. I can't emphasize how huge of a hurdle we've cleared by finding an off-the-shelf catalyst. Now, something I've been exploring is alternative solvents. There are actually two solvents used in our sodium production process: the reaction solvent that we actually perform the sodium production reaction in, and the purification solvent where we separate sodium from the leftover magnesium as well as tiny bits of magnesium oxide. For the reaction solvent, we're currently using mineral oil or baby oil, and to be honest, I don't think we're going to get much cheaper than that. But maybe we can find a solvent that runs the reaction much faster. A slightly higher expense would be justified in that case. Now for the purification solvent, we're using dioxane. Dioxane is easy to make for the amateur, and we in fact did so ourselves in a previous video. But because it's slightly carcinogenic, it would be preferable to find an alternative. Granted, substances like paint thinner and gasoline are probably even more carcinogenic, but still we want to try and reduce our exposure. Anyway, it would be awesome if we could find a single solvent that does both reaction and purification. The reason why we can't use dioxane for the sodium production reaction is that the boiling point is too low. We need at least 160 Celsius before the reaction even starts. At 101 degrees Celsius, the boiling point of dioxane is just not enough. A higher pressure might work, but the dangers aren't worth it for the amateur. Anyway, a solvent I've been looking at is another essential oil, Eucalyptol. It's very easy to buy, although it's somewhat expensive since we're using it as a solvent. It has a nice high boiling point of 176 Celsius. While this is lower than our ideal temperature of 200 Celsius, it should at least start. What's most interesting is that it has a bridging ether group. This makes Eucalyptol a somewhat polar solvent, and according to our mechanism, most of the active species are polar, so a polar solvent should speed up the reaction. The ether group also makes Eucalyptol an ethereal solvent similar to dioxane. So perhaps we can replicate the purifying properties as well. Okay, enough talk, let's actually give it a try. And now, Eucalyptol essential oil is not pure Eucalyptol. It's usually just 80% or so Eucalyptol. So before we can do our testing, we need to purify it ourselves. So to my 500 milliliters of Eucalyptol, I'm adding in 10 grams of sodium metal. Then I set up a reflux condenser and turned on stirring and heating to reflux. What I'm doing is reacting the sodium with any impurities that can react with sodium. If it reacts with sodium, then we don't want it, and if it doesn't, that doesn't matter. Now I know it seems circular to use sodium to purify a solvent with the intention of making sodium, but right now we're just researching Eucalyptol, and if it does work, we can figure out alternative purification processes later. Anyway, I left the Eucalyptol to reflux overnight. The next day, I rearranged the apparatus to a distillation apparatus and distilled off the Eucalyptol. Anything that was destroyed by sodium would be left behind. Now after I had distilled Eucalyptol, I decided to take a sample of 100 milliliters and reflux it with 3 grams of sodium metal. I wanted to see if there were any leftover impurities or if the Eucalyptol itself slowly reacted with sodium. You might not remember, but several months ago when we began this project, it was determined that tetrahydronaphthalene could not be used as solvent because it very slowly reacted with sodium to produce tar. It was slow enough not to be noticed by myself or other amateurs during our early potassium work, but was severely detrimental for making sodium. Unfortunately, after a few hours I started to see a color change. Either there were impurities or Eucalyptol was reacting. So I refluxed the Eucalyptol stock again over sodium overnight and again distilled it. Once again I ran the test and again it was a failure. Looks like the Eucalyptol itself reacts with sodium. This is not good. But I noticed the sodium still remained shiny rather than be covered with tar. The side products of this decomposition seem to be different than with tetrahydronaphthalene. While decomposition would certainly lower our sodium yield, maybe we can still use a solvent anyway. So I decide to run the sodium production reaction using a half-scale setup and a menthol catalyst. I went through the drying and startup cycles as usual, and interestingly enough, I got successful hydrogen formation, so it seemed like it was working. Maybe Eucalyptol was viable after all. Now normally this would take around 30 to 40 hours to finish using a menthol catalyst, but I noticed the reaction becoming very slow at just 14 hours. Maybe most of it reacted, but I waited until gas formation stopped completely at 24 hours to be certain. After cooling, I decanted the slurry and it looks like we got sodium. This is the first working alternative solvent to mineral oil, and it works even faster, completing the reaction in 14 to 24 hours. This gives some evidence that a polar solvent helps to speed up the reaction, and we should look for that property in future alternative solvents. Now looking at the sodium, I can see that magnesium is still attached to it. So as a purification solvent, it doesn't seem to be working in situ. But maybe the excessive amount of magnesium oxide byproducts was interfering. So I added in fresh eucalyptol and refluxed it like I would with dioxane. But after running it for 4 hours, it was clear it wasn't working. We can see the metal is still badly shaped, indicating magnesium embed in it. I then added dioxane this time and refluxed it, and the magnesium separated out with the same efficiency as dioxane always provided. I decanted off the sodium, and we can see from the magnesium left behind that Eucalyptol was not very effective if dioxane was able to remove this much. So it's clear that Eucalyptol fails as a purification solvent. But we did learn something. The fact that an ethereal solvent fails to purify sodium means that ether functionality alone isn't enough. Dioxane with its 2 ether groups might be special because it has chelating properties that Eucalyptol does not have. More testing will still need to be done, but we can start constructing a theory on that now that we have the Eucalyptol results. Anyway, as a reaction solvent, Eucalyptol works very well, and we even got 13.9 grams or about 94% yield. So the decomposition must be happening very slowly. But as a viable solvent for the amateur, I think Eucalyptol isn't acceptable. Without the crucial sodium purification property, Eucalyptol's only merit is that it's faster. But considering how expensive it is, and that we need to purify it first, makes it less cost and labor effective than simply buying a better catalyst. Nonetheless, I still think these couple of weeks were time well spent since the Eucalyptol results help us learn more about the reaction conditions and mechanisms. Anyway, thanks for watching. Progress on the sodium project continues.